Welcome to this scientific lecture on one of the most counterintuitive phenomena in fluid dynamics, the reversed mixing paradox. Here's the paradox. In our everyday experience, larger systems with more turbulence mix better. A bucket with a stirrer mixes faster than a thimble. But at microscales, this intuition completely reverses. A tiny moving droplet can mix faster than a large stirred tank. Classically, we think that mixing improves with scale. A large industrial reactor with powerful stirrers creates turbulent eddies that rapidly homogenize fluids. This is what we observe in our macroscale world. On the left, we have a large tank with vigorous stirring creating turbulent flow. On the right, a tiny thimble with fluid that appears static. We would expect the tank to mix much faster. Let's start by understanding mixing at different scales. At the macroscale, in pipes with diameters of centimeters or larger, mixing is relatively easy. The key parameter is the Reynolds number. When the Reynolds number exceeds about 2300, flow becomes turbulent. Turbulence creates chaotic eddies that rapidly mix fluids. The Reynolds number equals density ρ times velocity v times diameter d divided by viscosity mu. This dimensionless number tells us whether flow is laminar or turbulent. Let's calculate a numerical example. Consider water flowing in a 1 centimeter diameter pipe at 1 meter per second. Water has a density of 1,000 kilograms per cubic meter and a viscosity of 0.001 Pascal seconds. Plugging in the numbers, we get a Reynolds number of 10,000. This is highly turbulent flow, which means excellent mixing. In turbulent flow, chaotic eddies of various sizes stretch and fold fluid elements. This creates rapid mixing across the pipe cross-section. Now let's shrink down to microchannels. These are channels with diameters of tens to hundreds of micrometers. Here, mixing becomes extremely difficult. Why does mixing become so hard? Because the Reynolds number becomes very small. Remember, Reynolds number scales with the diameter d. Let's calculate. Consider water in a 100 micrometer channel flowing at 1 millimeter per second. The diameter is 100 times 10 to the negative 6 meters, and velocity is 0.001 meters per second. The Reynolds number is only 0.1. This is extremely laminar flow. There is no turbulence whatsoever. In laminar flow, fluid moves in parallel streamlines. There are no eddies or turbulence. The red and blue streams flow side by side without mixing. In purely laminar flow, the only mixing mechanism is molecular diffusion. But diffusion is painfully slow. The diffusion timescales as T equals L squared divided by D molecular, where L is the distance and D molecular is the molecular diffusion coefficient. For small molecules in water, the molecular diffusion coefficient is typically around 10 to the negative 9 square meters per second. D molecular approximately equals 10 to the negative 9 square meters per second. How long does it take to diffuse across a 100 micrometer channel? Plugging in, we get 10 seconds. That's extremely slow for industrial processes. You might ask, why can't we just stir the microchannel to create turbulence? The answer is that viscosity completely dominates at small scales. To create turbulence, inertial forces must overcome viscous forces. But at microscales, viscous forces are overwhelming. Viscous forces scale with L squared, while inertial forces scale with L cubed. As you shrink, viscous forces win. Think of it this way. Trying to create turbulence in a microchannel is like trying to stir honey with a toothpick. The viscosity completely damps out any turbulent motion. Now here's where the paradox appears. When we form tiny droplets, typically 10 to 100 micrometers in diameter, and move them through a channel, something amazing happens. These tiny moving droplets can mix faster than large stirred tanks. A thimble-sized droplet mixes better than a bucket. This seems to violate everything we just learned. On the left, a moving droplet develops internal circulation patterns called vortices. On the right, a stationary droplet with no mixing. The secret to this paradox is internal recirculation. When a droplet moves through a channel, it develops internal vortex flows. As the droplet moves, there is shear at the interface between the droplet and the surrounding fluid. This shear drives internal circulation within the droplet. The internal velocity is proportional to the external velocity times the ratio of external to internal viscosities. These internal vortices continuously stretch and fold fluid elements inside the droplet. This creates exponential growth in the interfacial area between different fluid regions. Let's quantify this. How fast is the mixing in a moving microdroplet? The mixing is characterized by the Péclet number, which compares advection to diffusion. The Péclet number equals the circulation velocity times the droplet radius r divided by the molecular diffusion coefficient. For a droplet with internal recirculation, the mixing time is dramatically reduced. The mixing time is approximately r divided by the circulation velocity. Notice this scales linearly with r, not r squared like pure diffusion. Let's do a numerical example. Consider a 50 micrometer diameter droplet moving at 1 millimeter per second. The radius is 25 micrometers. External velocity is 1 millimeter per second. The internal circulation velocity is typically about 10% of the external velocity, so about 100 micrometers per second. The mixing time is 0.25 seconds. This is 40 times faster than pure diffusion across the same distance. Now let's compare this to a large stirred tank. How long does it take to mix a 1-liter tank with a typical stir? For a 1-liter tank, with a typical magnetic stirrer or impeller, mixing times are typically 10 to 100 seconds, depending on viscosity and stirrer speed. So the tiny droplet mixes 40 to 400 times faster per unit volume than the large tank. This is the heart of the paradox. Let me give you a vivid analogy. Imagine you need to mix cream into coffee. In a bucket, even with vigorous stirring, it takes 30 seconds to fully mix. But in a thimble, just rolling it around mixes everything in 1 second. The thimble wins. Why does the thimble win? Because the diffusion distances are tiny. The circulation brings every fluid element close to every other element very quickly. In the bucket, there are large dead zones far from the stirrer where mixing is slow. The thimble has no dead zones. Everything is always circulating. Let's look at the key scaling laws that explain this paradox. Pure diffusion timescales as L squared. This is the worst case. Turbulent mixing timescales as L to the 2/3 power. This is better, but requires high Reynolds number. Chaotic advection with internal vortice scales only logarithmically with Péclet number. This is the best possible mixing. Microdroplets achieve chaotic advection even at very low Reynolds numbers. This is the key insight. You might ask, if droplets can have internal vortices at low Reynolds number, why don't we see vortices in microchannels? The answer is boundary conditions. A solid wall imposes a no-slip condition that completely prevents vortex formation. But a droplet interface is not rigid. It allows tangential motion. The fluids can slip past each other at the interface, which is what drives the internal circulation. In a solid channel, the walls enforce no-slip boundary conditions. No vortices can form. The flow must be parallel near the walls. What are the practical implications of this reversed mixing paradox? First implication. For chemical reactions requiring fast mixing, microfluidic devices use droplet-based systems rather than continuous flow channels. Second, lab-on-a-chip devices for medical diagnostics exploit this effect. Tiny droplets can perform rapid assays that would take minutes in a test tube. Third, pharmaceutical manufacturing is starting to use microdroplet reactors for precise synthesis. Each droplet is a tiny reactor with excellent mixing. Fourth, nature has been using this principle for billions of years. Cellular organelles and vesicles are essentially microdroplets with excellent internal mixing. For those interested in the deeper mathematics, the mixing in droplets is characterized by positive Lyapunov exponents. The Lyapunov exponent lambda equals the limit as t goes to infinity of 1 over t times the natural log of the ratio of final to initial separation of fluid elements. A positive Lyapunov exponent means fluid elements separate exponentially fast. This is chaotic mixing. The mixing time is proportional to 1 over lambda times the natural log of the Péclet number. This is far superior to diffusion or even turbulent mixing. In recirculating droplets, the Lyapunov exponent is approximately equal to the circulation rate. This gives rapid chaotic mixing. There's another surprising aspect, energy efficiency. Which is more energy efficient, the large tank or the tiny droplet? A large stirred tank requires watts to kilowatts of power to maintain turbulent mixing. Moving a microdroplet requires only microwatts to milliwatts of power. The energy per unit volume per unit time is comparable, but the absolute energy is tiny. When you account for the faster mixing time, droplets are roughly 1,000 times more energy efficient per volume mixed. You might wonder, if droplets are so superior, why do we still use large stirred tanks? The main disadvantage is throughput. A single droplet is tiny. To process liters of material, you need millions of droplets. Modern microfluidic devices solve this by parallelization. You can process thousands of droplets simultaneously in a droplet array. But for truly bulk industrial processes requiring tons of material, conventional stirred tanks are still necessary. The paradox applies at research and pharmaceutical scales, not refinery scales. Let me summarize the three regimes we've discussed. Regime 1. Macroscale pipes with Reynolds number above 2300 have turbulent flow and easy mixing. Regime 2. Microchannels with Reynolds number below 1 have purely laminar flow and nearly impossible mixing by diffusion only. Regime 3. Moving microdroplets with internal recirculation achieve the best mixing despite low Reynolds number. The reversed paradox is that the smallest system mixes the fastest because it exploits chaotic advection. The thimble truly does mix better than the bucket. This is not intuition, but rigorous fluid dynamics. What can we learn from this paradox? First, our intuition, built from everyday macroscopic experience, can completely fail at microscales. We must rely on quantitative analysis. Second, dimensionless numbers like Reynolds and Péclet numbers are the true governors of behavior, not absolute sizes or speeds. Third, nature often finds elegant solutions that we overlook. Cells have been using this principle for eons. Finally, engineering at microscales requires fundamentally new thinking. What works at large scales fails miserably. What seems impossible becomes easy.